Thank you very much. Yeah, hi everybody. So unfortunately, we are still in the process of setting up somehow the mathematical formalism I need to present you, as I think, very interesting theorems on quantum Hall physics. But I hope that if I will be able to do the program I planned for today, that we will have one interesting, physically interesting theorem today already. Okay. So, but now we are still dealing a bit with the formalism. Since I don't expect for most of you to be familiar with it, I just wanted to introduce it in such a way that you at least get an idea of what is going on. So remember, we are modeling infinitely extended Fermi systems on lattices. And in particular, we defined the algebra of quasi-local observables. So these are basically operators on stock space that are more or less supported locally in space. And then we also defined subspaces, Cauchy spaces A infinity and B infinity. This A infinity are observables that are almost local, that in a sense decay very fast. We made this precise last time. And these B infinity space are rapidly decaying interactions. And maybe the best way to think about it is a sum of local terms by X that are in this space. Each summit is in this space, localized nicely near X. And of course, such a sum here, sum X by X, will not converge in the bizarre algebra A, but we can use it to define derivations on the algebra, and in particular, that means we can use it to define commutators with an observable A that is sufficiently localized, because this sum here with an A that is localized will converge, because if X is far away from the support of A, this commutator will decay very fast. Okay. So that means we have these derivations, these interactions defining derivations on the algebra. And okay, this is all, you can do this in much more generality. This is not necessarily just a very strong decay, but for us it will be useful that on this space, derivations generated by such interactions really act as linear continuous functions. This is what basically the inequality the bound down here. Okay, so the last general ingredient we need is now the idea that such derivations given by these kind of interactions, they define time evolution, Heisenberg time evolution on the algebra of quasi-local observables. And for us, it will be important to have the situation where think of this as the Hamiltonian. At the moment, it's the general time-dependent family of interactions. So I don't know why you see here. Sorry, you should think of this as time. So this is a time-dependent Hamiltonian defined on some real interval I. And this is the corresponding Heisenberg equation of motion for dynamics on this algebra, which is now not a unitary dynamic, but it's a family of automorphisms of the algebra. And since for time-dependent generators, we always have an initial time and a final time, or actually the other way around, we go from time u to time b. We have these two indices, and this is called the co-cycle because we have this usual composition rule here. Okay. So think of this as the unitary time of Heisenberg time evolution if you are on you're dealing with operators on Hilbert space. It's now time evolution given by automorphisms of the algebra. And this would be the Heisenberg equation of motion. The time derivative of the evolved A is given by applying the commutative for Hamiltonian to A. Okay. And we will say that such a automorphism family here is locally generated if this generator here is given by a family of interactions, time-dependent interactions that are in this nice space D infinity and are continuous in time. Good. And now one can show, and that's again a standard result that we can show under much weaker assumptions on this Hamiltonian generator here, that I mean that any such family of interactions that has these nice decay properties and is continuous in time generates a unique dynamics on the algebra. Okay. I will not say a bit about the proof, but not too much. And maybe one thing is, which is also standard actually, is that we can include here also the Lipschitz potential I mentioned last time, which are not bounded, but which are really on-site interactions, which live on single sites. This is still, this poses no problem to proving existence of dynamics in the infinite system, even if they are unbounded. Okay, what is true now under the special assumption that our generator has this nice decay properties is the following question. For us, it will be important to know if we start with an observable A, okay, this is here, that is nicely localized somewhere in space, as measured by this new X norm we introduced last time, then the time evolution will map actually this space into itself. So it will keep the nice localization properties, and we can also control the growth of the norm of this local norm of the observable A. So the statement here is that there exists a function depending on nu. I mean, nu is the polynomial decay we use in this norm. And depending on this, we might have here a polynomial in a function that is bounded by a polynomial in the difference of the time, so in the time span we evolve. Okay. Good. If you're used to standard Lieb-Robinson bounds, and so you might think this is a very weak statement, but it's sufficient for us. And I will say more about this in a second. And only a technical statement, not important. This function depends on the generator phi, on the generating family of Hamiltonians, only through a certain norm. So if we know that for family this norm is uniformly bounded, then we can choose a uniform function B. Okay, and the existence of dynamics on the infinite system is a non-trivial result, but a standard result, which is usually proved using Lieb-Robinson bounds in finite volume, and then to show that the dynamics has a thermodynamic limit. And let me not go into this too much. This is standard stuff you can find everywhere. The type of Lieb-Robinson bound really depends on the properties of the generator here. And it also depends actually, surprisingly, on whether you're looking at quantum spin systems or fermions. For quantum spin systems, they are better Lieb-Robinson bounds, at least in the situation we are looking at, than for fermion systems. So a Lieb-Robinson bound is a bound on, you take two observables, A and B. For fermions, one of them has to be even, so that we can look at commutators. You evolve one of the observables under Heisenberg evolution and compute the commutator with a different one. The idea here is that A is supported in X, B is supported in Y, and X and Y are disjoint. That's what you should have in mind. So that at time 0, if you don't evolve at all, this commutator will be 0. And the question is, how long does it take so that the evolved observable sees the other one? That's the Lieb-Robinson bound, and the bounds are that we use here, and which one can prove for fermions with such kind of interactions have this form. You see again, it's in this setting where for every nu, we are basically in this faster decay than any polynomial setting. 1 second. And what you see here, I put in red because this is what usually people consider most important and most interesting about these Lieb-Robinson bounds. It's the question, how far, at what speed does, so to say, I mean, this will be, this bound will be small as long as this difference is large. okay? And this difference is initially the square root of the distance, but it grows, or it shrinks, this number here, with time. And this is the Robinson velocity, but which does not have this meaning in this bound. So basically, this is for the expert what is called quadratic light cone. So it's not a linear light cone. We don't expand with linear speed, but the speed, so to say, the distance I can travel in a given time grows quadratically in time. But this is sufficient for. So there was a question. That's much stronger. Exactly. So as I said, you have these much more general, but if you look at the very general ones with just finite f norms, depending of course what the f is, but if you think about f being something polynomial, then you will not easily get this kind of light cone for any power. No, linear is much better than this. For linear light cone, in fermionic systems, at the moment, as far as I know, you need finite range interactions or exponentially decaying interactions. In quantum spin systems, it's a big difference. But you have to be very careful when comparing different bounds because there are many things entering. For example, here the size of y, or this polynomial in time up here. Yes, because otherwise we are looking at fermions. We could not look at commutators if we commute to odd operators. Even to odd operators that are supported on this term Z, they don't commute, they enter commute. Okay, so one of them has to be even for them to commute. Okay. I will actually at some point this will make really a bit of trouble, and I will come to this maybe today, otherwise. Okay, again, this is uniform here when you have some bounds on these now. So this is again just to give you an idea. This allows you first prove these Robinson bounds in finite volume. This allows you to prove existence of the dynamics in infinite volume. And then you also have these bounds in infinite volume. Okay, so what I now want to come to is something which is maybe not known to people working usually on spin systems. In the end, I told you we want to do this adiabatic proof on adiabatic theorem. What you have to do is what is called adiabatic perturbation theory. It's really writing down perturbation theories and determining order by order some coefficients in the perturbative series. So let me just to motivate the definition that comes by just looking at the very simple type of perturbation theory you can think of. Think of you have a self-adjoint matrix H0 that has an eigenvalue E0 and P0 is the spectral projection. And let's say it's simple and since the matrix, it will automatically be guessed. So now you perturb your Hamiltonian with a small phi, which is here also self-adjoint matrix. So it's you know that then there is then the eigenvalue will depend in an analytic way on epsilon, and the spectral projection in an analytic way on epsilon in a sufficiently small interval, as long as the gap doesn't close, so that T epsilon is the spectral projection of H epsilon for E epsilon. Now you want to compute P and P, or actually P in a perturbative way, this perturbed state. And to do this, you can make the answer. You know, I mean, it's obvious that at least for matrices, the P0 will change continuously. It will still be a rank 1 projection, so it will be just conjugating by a near identity unitary. And so we make this answer. We slightly tilt P0 to get the epsilon. The generator of this unitary we call F, expand in a power series in powers of epsilon. Since this should be near identity, this starts with a term which is linear in epsilon. And now the question is, if we want to determine this P epsilon, here this S epsilon in such a way that we get really the spectral projection of the perturbed operator, we only have to solve this equation. We have to determine P tilde in such a way that it commutes with H epsilon. That's the short story. So, and if we plug this answer in here, let me do this quickly. If you're interested, you see it on the slides online. It's nothing deep. You just compute. I mean, this is the commutator with this answer. You compute the commutator. You expand the operator H epsilon in powers of epsilon, which is very simple. It's given in this way. So you get a term H0 and epsilon phi. You expand this exponential. It's also very simple. You get a 1, which is the P0, or here the epsilon term, which is the linear term here in epsilon, which is the commutator with K1. You rephrase this again in terms of this Liouvillean notation, and you see you have to determine K1 in such a way that this bracket here is 0, so that this holds. And at least naively, I mean, these commutators we think as linear operators acting on spaces of operators. We just have to move this linear operator to the other side. So we have to determine K1 such that this commutator equals this given commutator, which is expressed only in terms of P naught, H naught, and the perturbation. Of course, the question is now, can we really invert this Liouvillean? And the answer is in general, no. But this is well understood, but I would like to somehow that you can understand the structure in the more abstract setting better. I would like to go very briefly through the question of inverting the Liouvillean. So in the setting we are now, in this motivation setting where we have a finite dimensional Hilbert space, we can really also give the space of bounded operators the structure of a Hilbert space, defining this inner product. And then the commutator with the self-adjoint operator, the Liouvillean here, is actually a linear map from operators to operators, or matrices to matrices, that is self-adjoint with respect to this inner product. This is a simple computation. I will not get you through. But that tells us, for a self-adjoint operator, we know that the range of the linear operator equals the orthogonal complement of the kernel, meaning that LH maps the kernel. Okay. So the orthogonal complement of the kernel, on that set, of course, the linear operator is injective, because we forget about the kernel. And in particular, it maps the orthogonal complement of the kernel to the range. But the range is the same, so we know this operator maps this set into itself, and it's invertible on this set. So this map is invertible now. So on this set, we can invert the Liouvillean. The problem is, of course, it's not so easy to complete this general inverse of the Liouvillean. So we add another observation. This will be also for everything I'm discussing very important. So let me also go through this here in the simple setting in some detail. So given the spectral projection P0 of H0, we can actually split any operator into a diagonal and an off-diagonal part. Think of this as writing the operator as a block matrix, the part on P and the part on P perp. These are the diagonal entries and the off-diagonal entries, trivially. Now, the next observation is that the kernel of the Liouvillean is certainly contained in the set of diagonal operators. Because kernel means we commute with A, but then we commute also with every spectral projection. So we have this inclusion, and for the orthogonal complement, we now see that the off-diagonal operators are in the orthogonal complement of the kernel. And hence, we know that on that set, the Liouvillean is invertible, so in particular also on that subspace, which, as we can easily check, is actually, again, mapped into off-diagonal operators. So now we have the Liouvillean restricted to the off-diagonal operators, but on that set, we can easily write down an explicit inverse, This is what we were aiming for. And the inverse is just, it equals the commutator with the so-called reduced resolvent, which is the resolvent. Of course, P0 is an eigenvalue, so the resolvent is not well defined. But if we project on the orthogonal complement of the eigenspace of E0, this is a well-defined bounded operator. I will not show you the computation, but you can do this very easily for matrices to see that this, on this set, inverts LH. And this is, of course, all very well known, so this is nothing new. Just you've seen it. So the inverse of LH on this set is the commutator with R0. So this is, again, a simple thing, of course, assuming that we can somehow determine the reduced resolvent. And actually, this operator R0 is really a bounded operator. Its norm is really the inverse of the size of the gap. That's why we basically will need now, in the infinite dimensional situation, we will need a gap for this to be really a bounded operator. So this was a crash course repetition of these ideas. So, yeah. Of the kernel of the Liouvillean, no. I mean, actually, I will really, what I need is exactly what I said, that I want to motivate that I want to invert the Liouvillean on off-diagonal operators, because this is what I need in perturbation theory, which is on this slide. Yes. Yeah, but in our case, H0 will not be an operator, so this is derivation. And and in particular, since we have the gap, I think there will be, forgive me, I mean, we can talk about later, but this will not be, what is really relevant is, in perturbation theory, we want to find a K1 that solves this equation. Okay. Yeah, but we will have, you were not here last time, we will have locally unique depth ground state. So there will be, in the DNS representation, we will have a unique depth ground state, so nothing like this will happen. Actually, also in this discussion, I mentioned in the beginning on the slides, I didn't say it, that we assume it's a simple eigenvalue for all this discussion to avoid everything which distracts us from the main things we want to do. So we want to solve this equation, but now we can just define LK1 as we replace this LH1 by LR0. Why? Because if we take LK1 in this form, this is LR0, but the commutator of P0 with phi is an off-diagonal operator. So on that operator, this guy agrees with the inverse Liouvillean. We solve the equation, we determine the first order part in our expansion. So this is the motivation for trying to invert the Liouvillean also in this algebraic setting, in this infinite volume system. So we also want to do some type of derivation theory. Okay, now the question is, of course, how to do this on for our Liouvillean on the quasi-local algebra. And we want to do it again for an H that has a gapped ground state in the sense I introduced, which is called also locally unique gapped ground state. And the first idea would be, of course, go to a representation where we again have a Hilbert space. And probably most of you have seen this before. If not, let me briefly tell you that given a state on the quasi-local algebra, or actually on any CSAR algebra, this is very general here, there exists a distinguished representation of the algebra on a Hilbert space H. So the representation pi and the Hilbert space, they all depend on omega. And this representation has also a special cyclic vector, which is called capital omega, such that we can write the evaluation of this state omega on any observable A as the inner product in this representing Hilbert space of phi of A with this vector state capital omega. We can basically map everything to a Hilbert space. That sounds very nice. So this triple is called the GNF triple, and it's unique up to unitary equivalence. This is a very general statement. Now, okay. Now, what happens? What can we say more about this GNF representation if we know that our state is a gap ground state for Hamiltonian or Liouvillean LH. Remember, this was the gap condition. I will not go through it again. But if we know omega is a gap ground state for some Hamiltonian, then actually more is known. Namely, that in this GNF representation, we can represent H, this infinite volume interaction, as a self-adjoint operator, H omega, which is non-negative and has this vector omega, capital omega, as an eigenvector for the eigenvalue 0. And on the complement of this, the operator is larger than G. So basically, this special vector capital omega is a 0 eigenvalue, eigenvector for H, and H has a gap above 0 size at least G. So we are now in a setting where we have an self-adjoint operator with a non-degenerate simple eigenvalue. Okay. Yeah. But it's not important for what I'm writing here in the end. This is true. I mean, of course, this is not true if we don't have a gap. The rest will be true. But it will be important for us to invert the Liouvillean. Let's see. The gap is very important. Without the gap, the physics will not be the same. Good. But this statement up to this is true without gap. And actually also the group generated by this Liouvillean is the unitary group generated by this GNF Hamiltonian on the GNF Hilbert space. Okay, so we can map everything there. So that seems nice. Perfect. Let's do perturbation theory in the GNF space. Problem. It's not a good idea if we're interested in perturbations that act globally everywhere. Because then, if the perturbed state and the unperturbed state, their GNF representations will not be unitarily equivalent. We cannot stay in the same Hilbert space into perturbation theory. This only, I mean, in general, this will be only true if the perturbation acts it's a quasi-local perturbation. If you really perturb the system only locally in some small region, then we can do everything in GNF and there's no problem. But we are interested in global perturbations, like applying a global field or other things. So we cannot proceed in the GNF representation, which will turn out useful anyway. So we have to find a way to invert the Liouvillean on the level of the algebra without going to GNF. Or at least that will be the strategy. Good. And there is actually, this has been worked out. I again first suggested by Matthew Hastings, or actually also worked out. But then in a paper by Bachmann, Michalakis, Naftagale, and Sims, they worked out the details and the proofs and so on of this construction. This was all in finite volume. So it's actually still in a finite volume. It's still in the Hilbert space setting. But the point is to do it uniformly in the volume, which was the difficult thing. If you use the commutator with a reduced resolvent, that works in the setting, but this will not have nice uniform bounds and locality properties. So you had to modify it already there. And then it was worked out later by Moon and Ogata in infinite volume in the setting we are looking at for spin systems. So how does it work? And this will be an important ingredient to our analysis. And that's a nice tool which has been used since then in extremely many different applications. So that's a really nice tool because doing perturbation theory is always nice. Being able to invert a Liouvillean is always useful. So the construction uses a function WG, which will not be uniquely specified, but the properties of the function are sufficient to not care about how it really looks like. This is what we will use. We will pick some WG, and the result will not depend on this choice. That is non-negative, normalized, and even as a function on R, integrable. And actually, this comes with a G, which is really the gap. It depends on the gap how we choose it. Why? Because we choose in such a way that the Fourier transform of WG is supported in an interval minus BG around 0. And the other condition is that this function decays at infinity in space faster than any inverse polynomial. Such functions obviously exist. It's very simple. The infinity function supported on that set that is positive and normalized to 1. Okay, and then one defines, going back to Hastings, a posteriori, the idea is not very difficult. This map again on almost local operators in our algebra, given a derivation H, just by looking at the time evolution. So this is the automorphism group generated by LH applied to A, doing this one integral and another integral against this function WG. Of course, here you probably don't see why you do it. I will show you in a second why. But it's easy to see that this is well defined with what I showed you before, because we saw if A is in here and H is the B infinity interaction, then this will, the local norms of these guys will grow at most polynomially. So if you integrate this against a function that decays faster than any polynomial, this integral is obviously convergent. And using this I operation, the I stands for inverse. This will be the inverse of the Liouvillean. This I operation, we also define now the off-diagonal part of an operator by just composing I with the Liouvillean. This minus I, I don't know, for historical reasons. I could also include this in the map capital I, but people didn't, so I also don't. And the diagonal part as the rest of the operation. And yeah, it's with what I showed you before, very easy to see that these three maps are well-defined linear continuous maps on our algebra, on our space of almost localized observables. Good. So the interesting thing now is that the map does what we really want. First of all, it gives us an off-diagonal part of observables in the following sense. Off-diagonal before was always with respect to the ground state projection. Now it's with respect to the gap ground to a ground state of H. So for this, I actually also don't need the gap, but no, I do. I'm sorry. No. Here we need the gap. So omega is the gap ground state of LH. Then omega of, for any observable, omega of the off-diagonal part will be 0, and omega of A will be given by omega of the diagonal part. So that's the intuition why we call it off-diagonal diagonal part with respect to the ground state. Moreover, and this is something we will also have to use a lot, if you take the expectation of a diagonal operator times any operator, then the expectation factorizes. And thus, from this, you can conclude, or in the other way, if you put in the definition of diagonal, you see that if we take the commutator of the operators and the expectation, we can put on one, or actually also on both of them, an off-diagonal without changing the expectation. Okay? If you write this down again with replacing omega by the trace against P naught a projection, these are all obvious algebraic relations, and they still hold in this setting. One thing I should really say is, this is an extremely important property that this I does not destroy locality property. If we would in finite volume, which we could do, instead of I take the commutator with the reduced resolvent, there would be no way on earth to prove anything like this. So the key idea was to replace the reduced resolvent by this integral using the Robinson bounds or locality properties of the time evolution. Okay, and now this again allows us now to solve this this problem, this inverting the Liouvillean problem on the algebraic level. This is the problem we want to solve. I rewrite this now in terms of expectation with respect to a state defined by P naught in the algebraic language. We have to solve this equation, and then you see if we pick K1 equal I phi, then it will solve this equation. So if I put here for K1 the I, then this guy here is by definition the off-diagonal part of phi up to an I, and then by the star equation we can just remove the off-diagonal and we get what we want. So that will be the type of computations we have to do. Now, of course, later on our perturbation will not be an element of the algebra. It will be, again, a different interaction supported everywhere. So what we really have to do is we have to also do these kind of definitions, not only for elements of the algebra, but also for interactions, prove the corresponding statement. I don't show this to you. I mean, this is actually what makes some of these papers very long, but the idea is the same. So in the end, the upshot was that we can invert the Liouvillean in a way that respects the locality structure in our problem. Okay, I wanted to show you the proof, but since I'm so much behind, the proof is here. The proof is very simple. So the proof of the previous theorem that the I does the job. So the first thing we wanted to show is omega of f of a off diagonal is 0. Putting here the definition, we see this is obvious because omega is the ground state of H, so it's invariant under the dynamics generated by H. So omega composed with LH is always 0. That is trivial. The other thing is less trivial, but here we can actually represent this expression we would like to understand in the GNS representation. So what we do is we write out the definition of A diagonal, A off diagonal. We write the integrand here in the GNS representation because of the additional LH we get in here. We can write it as a derivative. So we can do the first integral and get this really explicitly do the first integral, get that expression. So this here does not depend on T. Omega W integrates to 1, as I told you. The positive integrates to 1. So this gives just this term. In this term, the group acting on omega. Remember, omega is an eigenvalue of H with eigenvalue 0, so we can forget about this part. So this gives us just the Fourier transform of W evaluated of H by the functional calculus. Omega W is a very nice function, so there's no problem with this. But now comes the trick. W hat was supported in an interval of size G around 0. So this is, if H has a gap of size G at least, this is a spectral projection on 0. 0 eigenvalue omega is unique. So this guy is just a projection on omega, which we can put in here. So we get the factorization. And then you see immediately from this, the claims I made follow immediately. Okay. So this is one of the tricks which allow to do all these things. And yeah, I wanted to show you. Good. Now I'm ready with the second part of my course. So actually the next thing I was less optimistic, so these are a bit shorter. No, sorry. Oh no, this is correct. Yeah. So this is part 3. Now we would like to use this toolkit I presented to you to do first this type of adiabatic theorem, constructing the non-equilibrium almost stationary state, and then understand the Hall response in these kind of systems, the macroscopic Hall response. Again, let me give you some motivation. I cannot assume that you're all familiar with the adiabatic theorem of quantum mechanics, so let me very briefly repeat what it says. So let's think again of finite dimensional Hilbert space. We neglect all the technicalities that come with unbounded operators and so on. So now let's think we have a Hamiltonian self-adjoint that is a function of time on some interval I. Let's say it's a smooth function of time, and it has at each time an eigenvalue E of t that is a simple eigenvalue, so it doesn't cross any other one, and let's denote the spectral projection by P of t. Yeah? So we have a time-dependent Hamiltonian with a time-dependent simple eigenspace, an eigenvalue, and everything very smoothly. Then the adiabatically scaled Schrödinger equation is the following equation for the state of the system. Or what we will be interested in will be solutions of this equation. So it's the von Neumann equation for the state. I don't write it as Schrödinger equation, but directly for the state. We initially start in the corresponding eigenspace of the operator, and then evolve according to the usual Schrödinger evolution, but with a prefactor eta there. And eta small means that basically on the microscopic time scale, we do this evolution very slowly, adiabatically. And the adiabatic theorem tells us that the solution of this equation, which I denote by rho eta, is well approximated by just taking the ground state at time t. Okay, so in norm, and the difference is of order eta. So basically, the adiabatic evolution, if you start in an eigenstate, follows the eigenstate changes, but the dynamics follows this changing eigenstate. That's standard adiabatic theorem. And we want something similar, so I have to tell you about a few ingredients to this problem. So actually, in this form, the nice form was proven by Kato in 1950. And it uses that also the spectral projection itself satisfies a dynamical equation of motion, a Schrödinger type equation of motion, or we like to write it in this form, namely just the parallel transport equation. So from a geometric point of view, we can think of these changing eigenspaces as a line bundle, rank 1 line bundle over the real line over time. And we just do parallel transport within this line bundle. But this geometric intuition will not be very important for us. So I just tell you that P of t solves this equation. And I tell you why in a second. What this capital T is, I will tell you in a second. But then his observation was, this is trivial, the first one. It's also trivial to observe that we can put here an H for free because H of t commutes with P of t. P of t is a spectral projection. But now this guy solves a Schrödinger equation with a Hamiltonian that is a small perturbation of H of t. This is usually called the adiabatic Hamiltonian. And now the proof of Kato just proceeds by comparing this Schrödinger evolution with this Schrödinger evolution, which is very simple. I mean, you just do the usual Duhamel, you take a time derivative, compare the generators, do one integration by parts, and you have the theorem. It's not difficult. But of course, you have to observe this first to come up with the idea. The original proof by who was it? I forgot. Top and yeah, you know. Okay, but this is, it proceeded differently. It didn't have this nice geometric picture. Okay, in any case, the t here you can just compute by taking the derivative of p and using p squared equals p. Then you will find this equation with this generator here. Oh. But maybe this is not important for us. So this is the idea. Use parallel transport and compare the two dynamical equations. Now, as I showed you in the yesterday actually an adiabatic theorem with error estimates that were not linear in eta, but of any order. So it didn't take long that people realized that you can improve this adiabatic approximation. And of course, you cannot improve I mean, this, it's very easy to see that this difference is in general of order eta. So you cannot just get a better bound here. That's not possible, but you can get a better bound by slightly tilting the spectral projection. Again, here by a unitary conjugation generated by an S that is of order eta. So the idea is to make a very small tilt of the projection in order to improve the approximation of the true solution to this so-called superadiabatic projection. This terminology was introduced by Michael Berry, but it's nice. Super is always nice. To improve the approximation so that the difference is really smaller than any order in any power of eta. Okay. And yeah, this is a shortcut. When I write this is a shortcut. For any n, there exists a constant Cn that this is bounded by Cn times the eta to n. No. The idea will be, this is not a non-trivial part, but the idea will be to have one S such that this is true, that you can for every n find a constant so that the right-hand side is bounded by the constant depending on n times epsilon to the n. But we don't want the S to depend on n. Of course, in the construction, you first make an S to order n, but then you do some sort of resummation. No, I mean, since you only want eta to infinity, you can do a very naive resummation. I mean, okay, I think this is a technical point. Let's talk in the break. Is it okay? It is, yeah, I think the idea is you have a series that does not converge, and you stop it at an n-dependent, at an epsilon-dependent step. So you pick an n of epsilon where you stop. This you can ever do, and depending on how this constant Cn grows, your function n of epsilon, when epsilon comes small, will grow very slowly. But this will always give you such a power. So it's really just to make it look nicer, so to have something which is, in the end, you can also think, for every n you go here. No, this is not in the paper by Nanchu. This is, I think, no, I mean, in the paper by Nanchu, I should say, I tried to, this was only a motivation. In the paper by Nanchu, actually, he assumes analytic dependence of the Hamiltonian on time, and he really gets exponential error. So he really can resum the series. I mean, the series is still not convergent. It cannot be convergent. You can compute, this is also a very nice problem, but long time ago, you can compute the non-adiabatic terms for very simple problems explicitly. So will never converge, but there you can resum in such a way that you can really get an exponential error estimate, because you can control the coefficient, the growth of the coefficient. Good. For us, it's certainly true in the many-body setting, nobody is even close to proving exponential estimates. So, and probably they don't hold. There are good reasons to think that this is not true here. Maybe stretched exponential. Okay. And the key feature is here that, again, we make a perturbative ansatz for this exponent. So this looks very much like the perturbation theory before. We put here in an asymptotic series, which will not converge in this case, but still we can try to solve for the Kn order by order. And it turns out here in this case that really the Kn at time t depends only locally on the Hamiltonian, namely on h of t and its time derivative. So to determine this object, you don't have to solve an evolution equation, a highly oscillatory evolution equation over a long time, but you can determine this locally. In particular, this guy will not depend on the history. It doesn't depend on where you came from. It really depends only what you're locally doing to the Hamiltonian. Okay. Good. And yeah, this is what I thought. So this is the standard adiabatic theorem of quantum mechanics. Now, let's apply it to many body systems. And again, there's a problem that that if you look at the, I didn't talk about the constants before, but if you look in the standard proof of the adiabatic theorem, that the norm difference between the two states and the instantaneous eigenstate is of order eta, but the constants contain the sup, among other things, the sup of the norm of h dot. Okay? But if we are now looking at n particle systems, h and also h dot, unless we look at very special local perturbations only, will grow proportional to the number of particles. So if we want to take a thermodynamic limit here, we are totally locked. And of course, you also know that for n particle systems, it's also a bad idea to try to, or it makes life much more difficult if you try to approximate the state really in norm. So there was a really, I mean, for my taste, extremely nice observation or paper, I mean, a technical paper by Bachmann, de Ruyck, and Fra in 2018, who proved an adiabatic theorem for many body systems, for lattice spin systems, where the bounds are uniform in the system size. However, they don't estimate, they don't get a norm approximation. That's basically almost impossible, uniform the number of sites, but they estimate expectations against local observables. So they only look locally at the state, where everything should behave like a finite system and the adiabatic theorem should hold. And indeed, they prove an adiabatic theorem of this type, comparing local expectations, but with constancy independent of the system size. This is set. So you take, it's a finite set. Sorry, I should have written this here. So this is the size of the finite set X enters here. So the larger the scale where you look, the worse the estimate. But if you choose to look on a certain scale, then it doesn't depend on how big the system will be if you make the system larger. So that's the idea. Okay. Good. And just for the history, when I read this and having 25 years ago worked on these kind of super adiabatic theorems, I thought, okay, let's write down a super adiabatic version with all these higher order corrections. This we did with Domenico Monaco in 2019. I have to say, if you know how this works, then going from their results to ours was not extremely hard. And actually, we also wanted, this was another reason to do it, we also wanted to do it for lattice kernels and other spin systems. Although, at least, this is done all for finite systems, uniformly with system size, and there, yeah, it's not too hard. Okay, but I should emphasize now that what I said until now is really the standard adiabatic theorem, which requires that the Hamiltonian on all scales for all times has a uniform gap. Okay, the gap doesn't flow. So we're really still in the setting where the gap cannot flow. But what we want to do, as I explained, we want to switch on perturbations that are macroscopic, that will definitely close the spectral gap. So what can we do? And now I would like to, okay, now I actually cut down on what I plan to do. I will show you the corresponding theorem and say only a few words on the proof. So what I want to show you now is what I call a super adiabatic theorem in the sense before, to any order in eta, but not for gap ground states, but for what we call the Lea state. And the situation, the setting is that now we have a time-dependent Hamiltonian or interaction in D infinity, depending smoothly on time. We put a topology here, so it's or a metric. This is a Cergy space. So it's clear what that means. And time-dependent family of Lipschitz potentials. And okay. We could also add here another time-dependent order epsilon. I forgot to put this uniformly bounded interaction. Okay, so we have a time-dependent Hamiltonian and time-dependent. No, that's the phi. Okay, sorry. Here should also be epsilon v plus epsilon phi. We can also add such a perturbation phi here, which is not a Lipschitz potential, but a bounded interaction. And we want to prove an adiabatic theorem for that. So now let's denote this two-parameter family of automorphisms group generated by the two-parameter family of Hamiltonian. Eta is the adiabatic parameter. Epsilon is the size of the perturbation. And we would like to find an approximation to the evolution generated by this two-parameter family. What we do assume is that H naught of T has for all time the gap ground state. But we do not assume that H of T has a gap ground state. So we perturb around this gap ground state with a perturbation that acts globally. Okay. And we have to make an assumption now actually on the regularity of the ground state, which I formulated here, which I basically we assume also that the ground state is in a certain sense differentiable as a function of time. This is a bit surprising, and if anybody of you has an idea how to prove this from the assumption that our gap stays open and the Hamiltonian is differentiable, I would be very interested in, because in the operator setting, once you know that the gap doesn't close and your operator has a certain regularity, the eigenvalue will have the same regularity. It's very easy to see. In this setting, nobody I asked has any idea how to prove this. No, it's an explicit assumption. When the application, in the application later on, when I apply to quantum Hall systems, I will prove this assumption. For this general statement, it's an explicit assumption. Okay? It will not be assumed later on for the models I look at. I have to prove it, and I will prove. It will be very simple in these models, you will see, but for the general, now we are in a very general setting. So this is, I show you the general theorem, and then we apply to this adiabatic switching of perturbation. Okay, and the theorem tells you, I'll try to make it very brief now and start here tomorrow again. That you can find such a generator of an automorphism group that is, so to say, local in time. That was this unitary transformation of our time-dependent ground state before. So a super adiabatic ground state that intertwines the true time evolution in the following sense. If you test it on a local observable A or on an almost local observable A, you compare this super adiabatic state, the super adiabatic approximation, with the true time evolution of our initial state. This is this guy. Then the error is, and now I put the n explicitly. Then for each n, you will find a constant Cn that this is bounded in this way. So now you will say, okay, there's an eta in the denominator, that's bad, but the exponent is the dimension that has a fixed exponent. So if you make n large enough, this will be small for eta and epsilon small. But of course, not uniformly in eta small if you make epsilon small. And this is something I will discuss tomorrow. So this, let me just finish with adding what I want to then go into more detail tomorrow. So the thing is that this generator here is really of order epsilon. So it's a small change of the ground state generated by a small global interaction. It's again local in time. It only depends on the Hamiltonian at time t. It doesn't know about the path. So that's important for our adiabatic switching. I told you we want to switch on the perturbation, but the place where we end up should not depend on how we exactly do the switching. And this will guarantee that basically the dynamics forgets about where it comes from, but only looks at where it is, the adiabatic dynamics. And this will be the near states if on some time interval our Hamiltonian is constant, doesn't change anymore. If we come to a time where we just stay constant, then this state does not depend on eta anymore and also does not depend on time anymore. It's just one state where we end up, and this is what we call then a near state, and it has the property that within this evolution where we are now, where things don't depend on time anymore, it approximates the full time evolution now with eta equal 1, because eta doesn't play any role anymore, up to terms smaller than any order of the time. These are these resonances, these many-body infinite volume resonances we construct that are invariant to all orders under the time. Okay, let me stop here, and tomorrow maybe discuss a little bit more this error estimate, and then show you how we apply it to linear design. Or actually, I will say a few things about this, the non-trivial ingredients to this. Thanks a lot.